A capacitor is basically like a short-term rechargeable battery. It's like a battery that can be quickly charged up and just as quickly discharged. And I can demonstrate that for you here. On this power supply, there's a large capacitor right here on this board. And I can charge this capacitor up by connecting it to this battery. And charge this guy up like this. It's now fully charged. It only takes a fraction of a second to charge the capacitor. Now when I connect the lamp to it, what you'll see is the lamp will glow shortly and then for a short time and then dim out as the capacitor discharges. Here, let me just do it one more time here. Ooh, ah. Charging up, discharging. Capacitor charging up, discharging. And actually, if I don't charge it through the lamp, if I charge it just directly off the battery, that's all it takes. Just a fraction of a second will completely charge the capacitor. So a capacitor is like a very short-term rechargeable battery that can be quickly charged up, but will also just as quickly discharge. Now, if you look at your capacitor, you will see that it is polarized. That is, there's a positive lead and a negative lead. And generally, the negative lead is marked on the side. You'll see like a little minus sign. Sometimes this is an arrow, like that. Okay, can you see it on your little capacitor that you have? I can show it to you. Well, here, I'll show you another one up close here. See, this is the minus side here. If I back up just a little bit here, get a better look at it. That's the negative side. The positive side is not marked, but there's a negative side. And you'll also notice that the positive lead is the longer of the two. You notice that one lead's longer than the other, and the positive lead is the longer of the two. That's so you can identify. The capacitor from the bottom of the board. When you have it mounted on a board, you can look at the bottom and see which side's the positive end and negative end. And that's real important because if you connect the capacitor backwards, it will blow up. Not maybe sometimes kind of blows up, not blows up, a little bit. It really blows up. It blows the heck up. Yeah.
Demonstration.
No, not demonstration. Not for now. But it's real important that you connect these properly. I'm always very paranoid when I'm working with capacitors. Make sure that you get it in there properly, because what's inside these capacitors is a couple of sheets of aluminum foil separated by some brown paper, and the paper is soaked in something called electrolyte. Say, Jeff, you got your tools there. Grab a pair of dikes so that I can cut one of these things open. I don't happen to have a pair with me. Danke. I'm going to cut this one open so you can kind of see what's inside. Kids, don't try this at home. In the bottom of this thing is like a rubber plug. Pop. There it is. And here's what's inside. Let me just show it to you up close on the camera here. Smell! If you look inside, here it is all rolled up. Now, let me just take the tape off here. Yeah, it was really important, Mel. You blew it. Okay. And let me just hold this out here so you can kind of see what it looks like. And I can unroll this paper.
Wait a minute, like this?
Well, here, you big babies. Here's the paper, and the what you see here is these two sheets of aluminum foil, and separating them is this paper soaked in something called electrolyte. The electrolyte is like the, you know, in your car battery, you know, the acid, that's electrolyte. Or in a dry cell battery, if you've ever seen a leaky dry cell, the stuff that's leaking out is electrolyte. Technically, what electrolyte is something that allows something called an ion to migrate. I don't know exactly what I'm talking about even. I don't care, because all I know is that if you hook these things up backwards, they blow up and send little bits of paper and foil all over the place. It just gets all over everything, and this makes a big mess. My high school electronics teacher told me of a guy, they nicknamed him Boomer because he was always putting these things in backwards. So be careful. Now this stuff, this electrolyte, ooh, it really stinks like hell, and it's all over my hands now, and it kind of burns a little bit. And so you should be careful with these things. You're not really supposed to pull them apart. But that's what they look like inside. And as I mentioned before, and as I demonstrated, basically they're like a short-term rechargeable battery. These capacitors are called electrolytic, L-Y-T-I-C, electrolytic capacitors. There are many different kinds of capacitors, but the type that we're mostly concerned with is the type that fails the most. If something never fails, I may never even tell you about it, because I don't care. If it doesn't fail, I don't care what it is or what it does. But the electrolytic capacitors do fail a lot. It's a very common failure, and I'll tell you more about this in just a little bit. And it's especially common in monitors and power supplies. We see a lot of capacitor failures. When a capacitor fails, sorry, let me back up a little bit. Capacitors are rated in microfarads. A capacitor is rated in microfarads. The more microfarads a capacitor has, the more of a charge it will store, the more of a charge it will hold. Now, actually, our unit of capacitance is really the farad, F-A-R-A-D. That's another one of those dead guy terms. In this case, it was named after a guy named Michael Faraday, a brilliant mathematician and electronic genius kind of guy. In fact, it's Michael Faraday that invented the electric motor and discovered electromagnetism and magnetic fields and all kinds of stuff. Really just amazing stuff. And so our unit of capacitance is the farad. Well, a 1 farad capacitor is huge. A 1 farad capacitor, depending on the voltage rating of it, is a gigantic, can be a giant thing. We actually use, and it's much bigger than anything we need in games, we actually use capacitors that are rated in millionths of a farad, microfarads. Now remember before when we were talking about the resistor, the metric prefix, the millions, mega, kilo times thousand, remember that? Well, we use real big things in electronics, and we use real itty-bitty teeny-weeny things as well. So we have mega, which means times 1 million. We have kilo, which means times 1,000. Those are our big things. Now we have itty-bitty things. We have milli things. Milli means divide by 1,000, or times 1/1000th, of course, same thing. And we have micro things. Like, for instance, we can have millivolts, milliamps, milliwatts. And we can have microamps and microvolts and micro things as well. And micro is divide by 1 million, or times 1/1,000,000th of something. And so our capacitors, the electrolytic capacitors that we use in games, the ones that fail a lot, are rated in millionths of a farad, microfarads, millionths of a farad. The one I gave you, I think, is like 100 microfarads, isn't it? If you look at it. Doesn't it say 100?
Yeah.
Okay. Well, we use a capital letter M for mega as an abbreviation. We use a lowercase m for milli. Wow, what are we going to do for micro? Now we're screwed because we only have two m's. We only got a capital M and a lowercase m. We have to use something else for million. What we usually do in this case is we go to the Greek alphabet. And we use the Greek letter mu, which looks like this. That's the Greek letter mu for microfarads. And so we abbreviate microfarads like this, mu f, microfarads. And if you look at the capacitor, like for instance this larger capacitor that I have here, oops, 3,300, you see the Greek letter mu, 3,300 microfarads. So you see the term microfarads abbreviated with the Greek letter mu. Anytime you see the mu in front of something, it means micro. For instance, I'll show you later, when we talk about monitors, we'll be talking about things in terms of microseconds. Microseconds. Millionths of a second, the Greek letter mu. But because the Greek letter mu looks a lot like our letter U, you'll sometimes see that as an abbreviation for microfarads. For instance, we might have a capacitor that's 3,300, like I just showed you, microfarads, the Greek letter mu, microfarads. And you'll see it on the schematic diagram and everything. We'll look at those shortly. You know, you might have a capacitor that's 2,000 microfarads. It might be abbreviated UF. Because the Greek letter mu looks so much like our letter U, you might see the term microfarads abbreviated UF. So if you've ever wondered what an UF is a microfarad. Or enough is enough, I guess, whatever. You might also see it abbreviated, you might have a 1,000 MFD microfarad. These things all mean the same thing. They'll be abbreviated all the same way. You could have a capacitor, might just say MF, and that doesn't mean mofo, that means microfarads. And you'll see it on the schematic, but usually the proper technical way is that they abbreviate it with the Greek letter mu, microfarads. The more microfarads a capacitor has, the more of a charge it can store. The more microfarads it has, the bigger, electrically speaking, it is. That is, the more of a charge it will store. For instance, the capacitor that I used to demonstrate that I charged up and then discharged it to show you the lamp deal. This was, I think, 18,000. Yeah, 18,000 microfarads. Typically, in a power supply, we have capacitors that are 3,300 microfarads, like the one I showed you. We use everything from a half a microfarad up to 18,000, 20,000 microfarads, all kinds of different values, and they do different things in different circuits. One of the ratings, so capacitors actually have two specifications. Electrolytic capacitor, well, all capacitors. One is its capacitance in microfarads. How many microfarads does the capacitor have? Is it 1 microfarad? Is it 10? Is it 4.7? Is it 1,000? Is it 3,300? How many microfarads does it have? The second rating of a capacitor is the voltage rating of the capacitor. The second rating is the voltage rating of a capacitor. What's the voltage rating on the cap that you have? It's 100 microfarads, 10 volts, isn't it? Okay. What the voltage rating means is the voltage rating of a capacitor is the maximum amount of voltage that the capacitor can handle. The voltage rating of a capacitor is not how much voltage it puts out. It only puts out what you put into it. The voltage rating of a capacitor is the maximum that capacitor can handle. For instance, if I take a 16 volt capacitor and charge it with a 6 volt battery, I only get 6 volts out of it. It's the maximum it can handle. You have to substitute parts a lot. When you have to substitute capacitors, you can always use a capacitor with a higher voltage rating. I do this a lot. For instance, I carry around these boxes here, and they're basically just like tackle boxes full of capacitors. It's just full of different kinds of capacitors. One common value that I use a lot is 10 microfarads. And in here I've got 10 microfarad, 200 volt capacitors. But a couple of weeks ago I had to fix a monitor in one of the classes, and I needed a 10 microfarad 16 volt capacitor. I used the 10 microfarad 200 volt. It works fine. Remember, it's the voltage rating of a cap isn't how much it puts out. It's not going to put out 200 volts. It's the maximum it can handle. So it's kind of just like in your automobile. Let's say you have a little Toyota or something, and your car battery is only this big. You could put a car battery in that's this big, you just won't be using all the capability of it. Same kind of thing. Okay? So you can always go up in voltage. In many cases, you can go up in microfarads as well, but you have to be careful about that. And at this point, you folks are not advanced enough to know what I'm talking about in terms of when you can do it. I'll show you later on, though. Primarily, for now, let's leave it at this. You can always use a capacitor with the same or higher voltage, but the number of microfarads should be the same when you change capacitors. For now, I will tell you places where you can actually get away with more capacitance, and it works perfectly okay. But capacitors fail. Electrolytic capacitors fail a lot. It's a pretty common failure. In fact, where parts like diodes and transistors and resistors can, theoretically, they can kind of last forever, a capacitor, an electrolytic capacitor, is guaranteed to fail eventually. 100% of the time, electrolytic capacitors eventually fail. And the reason for that is that the electrolyte, the stuff that's... What did I do with that torn apart capacitor?
I think you tossed it.
Did I toss it somewhere? Well, that electrolyte that I showed you, here it is. You know, that soaks the paper, and you can kind of see that it's wet. You can kind of see through it. The electrolyte eventually dries out. That's what happens. And heat is the thing that causes that to happen. Heat is the number one enemy of these things. They don't like to run hot at all. And you know that, especially in a monitor, it gets quite hot up there. Not only is it at the top of the game where all the heat rises, but the monitor itself generates heat. The picture tube gets hot, and some other stuff, a lot of resistors and things get hot in it. And as a result, electrolytic capacitors fail a lot. And when they fail, what happens is they become less of a capacitor. Let's say it starts out as 3,300 microfarads. Over a period of time, it loses its charge, loses its ability to hold a charge. It becomes a 3,000 microfarad. And then a couple of months later, it's only 2,500 microfarads. And then it becomes a 2,000 microfarad. You know, it just becomes less of a capacitor. Now, depending on what the circuit is that it's in, you'll see all kinds of different symptoms. In a monitor, it causes everything from a distorted picture, where you've probably seen this, where the picture is shrunken down at the top, squished at the top, and stretched at the bottom, or the sides of the picture are curvy, it just looks distorted. Those are capacitor failures. In a power supply, we'll see that there's lots of capacitor failures in power supplies, and it causes everything from a power supply that just doesn't work at all to a power supply that creates all kinds of strange electrical noise. Sometimes you've seen this on the screen where you see the video game playing, whatever the game is, and you see these diagonal lines very closely spaced, kind of drifting all around the screen. It's called herringbone interference. That comes from the bad capacitors in the power supply. We'll talk more about that on Wednesday. Now, fortunately for us, much of the time you can look at a capacitor and see if it's good or bad, which is really excellent. Much of the time you can just look at it and see if it's good or bad. And here's the kind of thing you're looking for. Number one, whoa, hey, avalanche. When you look at the capacitor, if you look at the top of it, do you see how the plastic coating is even all the way around the top? If you look at this plastic coating, this edge here, do you see how it evenly covers the top? If this is shrunk back, if this is pulled back at all, that capacitor is on its way out. What did I do with my back caps? Give that. You notice a couple of things about this cap. Number one, the plastic coating, you see how it's pulled back somewhat. It gets much worse than this, actually. I'm trying to get the reflections down here. If you see that, well, basically, if you see that the plastic coating, instead of coating the top like this, has pulled down like this, and you see the metal part, the whole disc on the top exposed, that's definitely bad. There's no question about that. Another thing you'll see is that the top will be domed. That is, the top is supposed to be perfectly flat. And if it's pooched out at all, it'll swell up. You can just barely see here that it's not exactly perfectly flat. You see how it's kind of domed a little bit. Not terribly. But if it's like domed at all on the top like a bad can of pork and beans, that's definitely bad. Oh, man. And then when it gets really bad, you see this. You see that the top is blown right open, and you talk about being domed. That's what I'm talking about right there. Now in this case, it's broken open. This is the safety vent. On the top of most capacitors these days, you'll see that the top is scored. And the reason that the top is scored is that's a safety vent so that and here you can see that see how the top is scored on this one. It's a safety vent so that when the capacitor does go bad, it just opens up and lets the pressure out. Instead of having this top sail off and become a missile, which is what happens, the safety vent just opens up and lets the pressure out. We have a hole in the door of our shop that's about the size of a dime. From you talking about, let's blow one up, let's blow one up. Well, that's exactly what happened in the shop, and the guy said, hey, I'm going to blow one up, and he put it over here, hooked it up backwards, and it shot, it was a good 10 feet over to the door, and just blasted a hole in it. So be careful, like your mom said, you can put your eye out with that thing. You got to really be careful with capacitors. It's entirely possible if you put them in backwards that they'll blow up.
How thick was that door?
Well, it was just a hollow core door. Granted, it was not. Hey, can you close that back door for me, please? So, it wasn't the thickest door in the world, but certainly if it hit you in the face or the eye, it would really, really hurt, to say the least. Now, capacitors. If a capacitor looks bad, and again, the three criteria is the top domed, is it curved at all on the top? Bad. It should be perfectly flat. Is the plastic coating on the top shrunk down at all? Bad. Or is that vent busted open? Obviously, that's bad. Then you definitely have to replace it, but sometimes capacitors look good when they really are bad. And unfortunately, you cannot use your digital multimeter to check capacitors. You have to have a capacitor meter. You have to have a special meter just for capacitors. Which is really a shame because a capacitor meter can cost you 60, 70, 80 bucks. I paid 150 for this one, but you can get them cheaper than that. And yet it only checks one thing, capacitors. And your meter, which only costs 40 bucks, or can only cost 40 bucks, checks everything else, which is really bizarre. But using the capacitor meters is really pretty simple. All you do is set the capacitor meter for whatever range you want, just like with the resistors. For instance, there's 2 microfarads, 20 microfarads, 200 microfarads, and so on. And all you have to do is jam the capacitor into the meter. For instance, it has these clips too, or you can just put it in here like this, making sure that you get the polarity right. I turn on the meter. Meter says that this is 110 microfarads. It's supposed to be 100 microfarads. It's 110. This capacitor is good. When capacitors fail, the number of microfarads is less. In other words, it's supposed to be, well, for instance, there's a common problem in a Hytron power supply. There's a 220 microfarad capacitor. fails all the time. It just fails, and I'll point that out to you later on. And you pull that out and you put it on the meter, and it says it's only 27 microfarads, and it's supposed to be 220, or it's 100 microfarads or something. If it shows you even 10% less than what it should be, it's definitely bad, or it's on its way out, one or the other. Because here's a new 100 microfarad, you can see it says 109, 110, it's 10% over. Usually, almost all electrolytic capacitors, when they're new, are about 10% over what they should be. That's good. That's good, because remember, when capacitors fail, they lose their ability, they lose their capacitance. So when I see one that's even at all lower than whatever's printed on the cap, I got to say, well, this thing's on its way out. Capacitors are usually not a catastrophic failure. Capacitors usually fail a little at a time. They start to get worse and worse and worse. And in a monitor, you see increasing amounts of distortion on the screen. In a power supply, for instance, in this one power supply, the Hytron style that I was mentioning before, it does the weirdest thing. You turn on the game and it doesn't come on right away. And then 5 minutes later, bing, it fires up by itself. And the first time I ever got this call, I went, you're wrong. I mean, the call was, yeah, the machine takes 5 minutes to warm up. Well, you know there ain't nothing in a game that takes 5 minutes to warm up normally. I'm going, no, you must be wrong. Really, man? No, really? Okay, I'll be right out there. And I go out there at the liquor store, and they got it unplaced. Plug it in. They say, you wait. Okay, it's like an Herringbone liquor store. You wait. Okay, fine. So, have a Coke. Okay, fine, have a Coke. Sure enough, it doesn't come on. I'm going, well, let me just fix it. No, you wait, you see. Okay. Yeah, 5 minutes later, boing, the thing fires right up. Bad capacitor. Capacitors are funny like that. Sometimes when they're cold, they won't work, but as they warm up, the problems go away. You see this on monitors a lot. When you first plug it in, it looks like crap. And then after it heats up, the sides straighten out a little bit, and it gets bright, and it looks okay. Those are typical capacitor failures. As we'll discuss later on in a monitor, very often when if you have bad caps, you want to change them all at once. And I'll give you a source for these capacitor kits where you can replace them all for a pretty reasonable price. In fact, by virtue of coming to the class, you get a 15% discount. So I'll tell you about that a little later on. Now, I want to show you one thing about checking capacitors with a digital multimeter. And the only reason I'm showing you this is to tell you not to do it. What will happen is you'll go back and you'll be talking to some kind of a hotshot, and you'll say, Randy's full of shit. You can check capacitors with your meter. Watch. Here's how you do it. Well, this is what they're talking about. And I just want to show you this to tell you not to do it. Here's what I mean. They'll put the meter on some kind of an ohm scale. They'll put it like on... They'll put the meter on like the 2K scale or something like that, and depending on the size of the capacitor, and put their meter leads across the cap, positive to positive, negative to negative, and watch the meter charge up. Oops, that's a little fast here. Let me go to a different range. They'll watch the capacitor charge up on the meter. 1, 2, 3.1, 3.3, 0.4, 6, 7, 8, 9, 4.6, 5. You can see that it's charging up. And I mean, the meter's changing. You can see it's increasing in numbers. Well, obviously, this capacitor is taking a charge. That's what they say. Well, it's taking a charge. It's good. Well, in a way, they are correct. Yes, it is definitely taking a charge. But unless you have another one of the same capacitor and a stopwatch so that you can tell how long it takes it to charge up, you don't know if it's the correct value. In other words, a 100 microfarad capacitor will charge up just like a 1,000 microfarad will. It just charges faster. So you need to be able to tell exactly how many microfarads it is. And so I strongly suggest that if you're going to do a lot of monitor repair, you get a capacitor meter. Now, you don't have to have one. In fact, I've only had one for the past few years, really, and I've repaired lots of monitors before I had a capacitor meter. But the only other way to check it out is by substitution. That is, if you have a shitload of capacitors in your shop and you think that capacitor is bad, pull it out, try sticking a new cap in. If the problem goes away, obviously that cap was bad. And that's the way I've been doing it for years, but it's a real hassle unless you have a lot of capacitors. Because you say, oh, I think that one's bad, you go drive over to the store, you pick up a capacitor, you come back and you stick it in, and shit, that's not it, you go get another one, and it's a hassle. For 80 bucks or whatever it's going to cost you for a capacitor meter, if you're doing a lot of monitor repair, especially because that's where we have a lot of cap failures, it's not a bad idea to have a capacitor meter. Quite frankly, though, when I have bad capacitors in a monitor, and again, we're going to discuss this in great detail on Thursday, I usually end up changing just about all of them anyway, on the theory that when one's going bad, they're all probably going bad because they're all the same age. We might as well get rid of them all. And so, you know, if you're a small operator, I definitely don't suggest you run out and buy a capacitor meter, as long as you have a source of capacitors. But capacitors, you do need to get a lot of them. We'll be talking about part sources later on. In your book, there's a whole list of places where you can get parts for a pretty reasonable price, and we'll talk more about those as we go through that. Okay, but that's capacitors. And again, they fail a lot, especially in monitors. We have a lot of cap failures in monitors.
Hi, welcome to the Arcade School. You know, today's video games and electronic pinball machines are really state-of-the-art computer sophistication. And quite frankly, that's left a lot of mechanics a little bewildered. How do you fix something when you can't see the stepper step? How do you fix something when you can't see the relays open and close? Well, in fact, in a way you can see the stepper step, and in a way you can see the relays open and close. But you can't use your eyes. You have to use a piece of test equipment. And the piece of test equipment you want to use is called a digital multimeter. This particular digital multimeter is made by a company called Beckman. It's the Beckman Tech 310. And like other digital multimeters, this particular meter can be used to measure AC and DC voltage, AC and DC current, and resistance. There's also a very special range on this meter. It's called the diode test range. By using the diode test range, which is built right into the meter, we can test diodes and transistors without having to buy a separate piece of test equipment to do it. During this lesson, we'll be taking a look at the digital multimeter and effective ways to use it to repair electronic games. Let's take a closer look at this extremely versatile piece of test equipment. The single selector knob in the center of the meter selects not only the function of the meter, that is, voltage, current, or resistance measurements, but also sets the maximum range for each individual setting. DC voltages as high as 1500 volts and AC voltages as high as 1000 volts can be measured with the meter. The meter can also measure resistances from as little as 1/10 of an ohm up to 20 million ohms. Although the meter has AC and DC current measurement capabilities, we don't measure current when repairing games, so we won't talk about the current settings. The meter also includes a special diode check function that's useful for checking all types of different semiconductors. We'll look at all these tests during this lesson. Well, one of the easiest tests that we can make with the meter is to measure the voltage of a battery. We use batteries all over the place in electronic games. For instance, this Williams video game uses a battery as a backup to maintain the bookkeeping information and the high score to date and that other important information that we don't want to lose when the game's turned off at night. So let's take a look at the voltage tests and see how we measure voltage using the digital multimeter. Start the test by inserting the black meter lead in the jack marked COM for common. Our black lead will always be placed in the common jack. On the left is a jack mark for volts and ohms. That's where we'll put our red meter lead. The next thing we have to do is set the meter to read DC volts. And here we've set it to the 2-volt range because the battery's voltage is only around 1.5 volts. There are 3 batteries in this Williams video game that maintain the bookkeeping information. They're installed in these battery holders right down here on the computer board. And they just slide in pretty easily, just like this. To measure the voltage of the battery, we'll take the red meter lead and touch it to the positive terminal of the battery and the black meter lead to the negative terminal of the battery. We can read the voltage right off the meter, approximately 1.3 volts. Of course, you won't be measuring the voltage of a battery nearly as often as you'll be measuring the 5-volt power supply in the game. That 5-volt power supply is really important. All of the computers in all of the games you work on require an exactly regulated 5-volt power supply to operate. In fact, it can only vary maybe, 1/4 volt either way. If the voltage drops down below 4.75 volts, or if it goes above 5.25 volts, the computer may malfunction. In fact, it may not work at all. There are other voltages as well. For instance, in the Defender game, there's a positive 12-volt power supply and even a minus 5-volt supply. That's right, we can have negative power supplies in a game just as often as we can see positive power supplies. Both supplies work approximately the same way. The only difference is that in a negative power supply, the flow of current is reversed. We'll measure both those power supplies, positive and negative, the same way with our meter. To make it easier for you to test the power supplies in a game, many manufacturers are now installing test points right on their printed circuit boards. Well, this makes your job real simple. For instance, here on this Tempest printed circuit board by Atari, there's a test point marked GND for ground, and we'll connect our black meter lead to this test point. There's also a 5-volt test point on the printed circuit board, and it's right here, right next to this red LED that is glowing to indicate that we do have the 5 volts to the printed circuit board. With the meter set to the 20-volt range and the red and black leads in place, we can see the meter reads exactly 5 volts. All games require a 5-volt power supply to operate, and a pinball machine is no different. In this pinball machine, the 5-volt test point is seen here. It's labeled Test Point 5 right on the printed circuit board. And with the red lead on the test point, we can read the voltage right off the meter, 5 volts. Don't forget to put your black lead on ground, like the ground braid or the special ground test point. Well, even if your game doesn't have 5-volt test points or ground test points, there's still a real easy way that you can check the 5 volts going to the computer board. Do you see how all the integrated circuits on the board are arranged in rows? And do you see how there's this heavy printed circuit board trace running up and down each side of the rows of chips? Well, one of these traces, or power rails as they're called, carries the 5 volts to all the ICs, and one carries the ground. By placing the meter leads across the power rails, we can read the voltage directly across it. And here we see that it's real close to 5 volts. It doesn't matter which lead you put where. If you accidentally reverse the meter leads, the meter will simply show a negative voltage. So you see, with the digital multimeter, you don't have to worry about accidentally reversing the leads. We can measure the voltage of alternating current just as easily as we can measure the voltage of a direct current source like a battery or a power supply. But instead of setting our meter to read DC volts, we'll set it to read AC volts. Say, for instance, we wanted to measure the voltage from a floor receptacle. Well, we know that that voltage is somewhere around 120 volts AC, so we'll set our meter to the 200 volt AC range. With the meter set on 200 volts and the red and black leads inserted into the AC receptacle here, we can measure the voltage and read it right off of the meter. In this case, it shows 117 volts. If I were to accidentally set the meter too low, say on the 20 volt range, the meter reads OL. Well, OL stands for overload, but that doesn't mean that I'm hurting the meter in any way at all. It simply means that the input voltage coming into the meter through the red and black leads here is higher than the setting here on the selector knob. In fact, I can actually rotate the selector knob through all of the ranges, including the resistance range, without fear of damaging the meter. The meter is fully protected or idiot-proofed against all kinds of accidental high voltage overloads. Well, if this were a conventional analog or needle type of meter, you'd see little wisps of smoke coming out of the back of the meter, and you could watch the needle peg to the right as the meter instantly destroyed itself. In this case, we don't have to worry about it because of that overload protection circuit that's built right into the meter. Now that we know how to measure DC voltage and AC voltage as well, let's take a look at another very important test that we can make with our meter. There are certain types of power supply failures that allow a small amount of alternating current to ride on top of the direct current. This condition is known as power supply hum or power supply ripple, and can generally be attributed to a bad filter capacitor. The filter capacitor is very important for a power supply because it assures that the power supply voltage remains absolutely pure and constant. When the power supply has excessive ripple in it, the computer may malfunction or it may not work at all. So let's take a look at what we'll see when we have a bad filter capacitor in a power supply. As long as the 5 volt supply remains constant, the computer works normally and displays the picture you see here. But if the capacitor fails, hum bars occur. These horizontal blue bars are known as hum bars and are a visual indication of a bad filter capacitor. When the capacitor fails, the power supply does not remain constant. That is, the voltage is constantly changing. When we measure the DC voltage of the power supply with our meter set on the 20 volt range, the supply reads 4.58 volts. That's because the meter averages the times when the voltage is up at 5 volts with the times that the voltage is allowed to drop lower due to the bad filter capacitor. Well, we can easily determine if this problem is low voltage or ripple by switching our meter to read AC volts. When we switch the meter to read AC volts and check the voltage again, we see that the meter reads 0.6 of a volt of AC ripple riding on top of the DC. It doesn't matter if the power supply is in a video game or a pinball machine like this. Ripple will still test the same way. When the voltage reads too low on your meter, switch your meter to read AC volts and look for that AC ripple. In this case, 1.6 volts of AC ripple riding on top of the 5 volt supply means that we have a ripple problem here, usually caused by a bad capacitor. In this case, though, we can trace the problem to a broken wire. The broken wire disconnects the capacitor and allows excessive ripple into the supply. This video connector carries the video signal from the computer, and we can check with our meter and see if this video signal is present by inserting the meter lead into the connector. The changing voltage that we read on the meter indicates that the video is present. The higher the voltage, the more of that particular color is appearing at that time on the front of the screen. In this case, we definitely have video.
Steve Dacus for Wicco. You've heard the old saying, time is money. That statement was true nearly 200 years ago when Ben Franklin first said it, and it's still true today, particularly in our business. This kind of thing costs you money. At Wicco, we've been in business over 40 years, creating the fastest, most efficient, up-to-the-minute means of giving you the good service and the products that you need. We have 5 distribution centers throughout the nation with everything that you'll need under one roof. And we have a pretty simple way of putting them under your roof. Our new catalog comes complete with diagrams, descriptions, and prices on everything that we sell. In the front cover, there's complete instructions on how to purchase, how to receive personal attention, and at the top is our Wicco guarantee of satisfaction on every item that we sell. At Wicco, we'd like you to become as familiar with our catalog as you are with our name. Chasing down the parts that you need can cost you your most valuable commodity, time. At Wicco, we believe we can save you time and money. We're Wicco, world's largest distributor of parts and supplies to the amusement, music, and vending industries.
The resistance setting of the meter can be used to check resistors like this. This is a 2 ohm resistor, so we'll set the meter on the 200 ohm scale. In this case, we can read resistances from as little as 1/10 of an ohm up to 200 ohms. When we place the leads across the resistor, we read 1.9 ohms, which is within the tolerance of the resistor. This is a 47 ohm resistor. Again, we can tell by the color code that it's 47 ohms. And when we place our meter leads across it, it reads 49.5 ohms. Because of the tolerance of the resistor, this is again within its limits. This is a 47,000 or 47K resistor. We can't use the 200 ohm scale to measure it, so we have to go up to the 200,000 or 200K scale. When we place our meter leads across this resistor, it reads 44.3, but it's not 44.3 ohms because the setting is on the K scale. This is actually 44.3 thousand ohms, or 44,300. This is a variable resistor, or potentiometer. This is a 25,000 ohm potentiometer. So we'll start our test by measuring between the 2 outside terminals and using the 200K scale of the meter. The meter shows 25,000 ohms. The second part of this test is to check between the center wiper connection and either side. We can now see the resistance change from a minimum of 0 ohms all the way up to the full scale value of 25,000 ohms as we rotate the wiper. A bad potentiometer will test OL between the 2 outside terminals, or will jump wildly as the potentiometer shaft is rotated. This is a good potentiometer. Pinball coils have a low resistance, so we'll test them on the 200 ohm scale. Speakers can also be tested by using the meter. Speakers should read between 4 and 16 ohms, so we'll use the 200 ohm scale to check the resistance right here. With the meter set on 200, we read approximately 8 ohms, 7.6. Fuses are also tested with the meter on the 200 ohm scale, but be very sure that when you place your meter leads across the fuse, you touch the fuse holder and not measure across the 2 end caps of the fuse. If the connection is bad between the fuse and the fuse holder, you won't know it unless you measure it this way. Also, it's important that you never simply look at a fuse to determine if it's good or bad. This fuse looks perfectly good. You see the fuse element inside looks complete. And yet, when we test it with our meter, the meter shows OL. Of course, that means that the fuse is open. It's a blown fuse. What we should see is this reading, just as you see here. So this fuse is open. It's no good. As with the fuse test, we test switches on the 200 ohm scale. When we depress the switch, we see a short circuit. When we let go of the switch, we see OL. This is a good switch. Diodes are semiconductors that act as one-way gates for current flow, and there's a special diode test range right here on the meter. The readings we should get for a diode are some reading in one direction and OL in the other. Normally, you will read between 0.5 and 0.9 in one direction, and OL when the leads are reversed. Occasionally, you may see some very large diodes like this one that will read slightly below 0.5. As long as we get an OL reading when the leads are reversed, the diode is good. Bad diodes look the same as good diodes. The only way to tell is with your meter. This one reads OL in one direction and OL when the leads are reversed, so this diode is open. But the most common diode failure that you'll see is a shorted diode like this. Transistors are also tested with the meter set to the diode test range. This is the base of the transistor, this is the emitter, and the case is the collector of the TO3 package. We'll start our test by putting the red meter lead on the base of the transistor. With the red lead on the base and the black lead on the emitter, we'll read a junction drop of between 0.5 and 0.9. Leaving the red lead on the base and touching the collector, we should see the same reading. Then we'll reverse the leads and place the black lead on the base. Again, we'll check from base to emitter. This time we should read OL. When we move the red lead to the collector, we should also read OL. Well, many people feel that this is a complete transistor test, but it's not. There's one very important test that you have to make before proclaiming that transistor to be good. Emitter to collector should read OL, and it should read OL in both directions, no matter which way you put your meter leads. This is a bad transistor with a typical failure. Base to emitter reads junction drop, base to collector as well. When we reverse the leads and put the black lead on the base to emitter, OL, and base to collector, OL. So far, so good. But when we make that final test from collector to emitter, look, the transistor is shorted, and it's shorted in both directions. Integrated circuits that belong to the TTL family are used quite often in games. When these ICs fail, very often their inputs or outputs will short out, and we can pick up this short with our meter set to the diode test range. This is the only test where we will ground the red meter lead and use our black meter lead to probe each of the pins. A good input or output should read a junction drop like this. But a bad input or output will usually show considerably lower reading like this. And finally, let's take a look at one more test. If the printed circuit board is shorted, you can't find the short circuit with your meter set to resistance. Look, no matter where we test the board, when we measure resistance across the power rails, the board appears shorted. It appears shorted everywhere because all the rails are tied together. The short will often be caused by one of these small capacitors which are wired directly across the power rails. They look like diodes, but they're capacitors. We can't find it with our meter set on resistance, but we can find the short if we move our meter selector to read voltage on the lowest DC range. Connect a battery to the power rails. Connect the ground lead to the ground test point and the red lead, which is connected to the positive terminal, to the 5-volt test point on the printed circuit board. What we're trying to do here is power the shorted board with the battery. Then take the meter and connect the meter leads to each individual power rail one at a time. As we get closer to the short circuit, we should see the voltage drop. Here it's 83. Here the reading is 55. Here it's 21. But here the voltage has gone up, so we've passed the problem. The short must be in this power rail here. Now we can move up and down the power rail to find the shorts. As I move in this direction, the voltage increases, so I'm going the wrong way. When I move the leads down toward the bottom of the board, the voltage decreases as I get closer and closer to the short circuit. If I pass the short circuit, the voltage will go up. And right here we see the voltage has started to rise, so I'm going to back up and move my leads back the other direction. By moving the leads back and forth like this, I can get down to the exact point where I find the short circuit. The lowest voltage will be the position of the shorted component. In this case, it's this capacitor. Well, that's it as far as our digital multimeter tests are concerned. And you can see that the digital multimeter is an extremely effective piece of test equipment, and you won't want to go anywhere without it. But that's all the time we have for now. So I'll see you next time at the